Hello everyone, I'm Nicolas Hulou from Aix-Marseille University, and today I will present you a novel contact model applied to a fingertip on an ultrasonic vibrating plate. I'm sure that you have all tried to put your finger on an annoying bell to stop its ringing. The compliance of the skin allows the contact to set on a large area in which vibration could travel and dissipate in viscous loss. This absorption is not limited to audible wavelength and could be extended to ultrasonic vibration. On ultrasonic haptic devices, which use glass vibration to reduce friction between the fingertip and the plate, we observe that the presence of a fingertip on its top impedes the vibration. More, the way the plate vibration is modified is affected by the force applied by the fingertip. We have chosen to use the mechanical impedance of the plate, which is the inverse of the admittance, to monitor these changes. The contacts have a multi-temporal behavior. One takes into account every individual oscillation and has a timescale around the vibration frequency, near 20 microseconds. The other one is in the timescale of the levitation phenomenon, which results from several oscillations. Within the frequency range of the ultrasonic vibration, around 30 kHz, the plate could be modeled as a second-order oscillator, which is excited by an activation force. Also, around the excitation frequency, the fingertip behavior could be modeled as a second-order dynamic system. The connection between these two bodies is made by the contact itself. The contact is modeled by a spring and a damper that represent the squeeze film pressure and the end asperity of the skin. While this whole length parameter model moves at the frequency of the plate oscillation, excited by the harmonic force, the external force and the contact force is dictated by time average behavior. The external force is simply the pressure force of the fingertip, and the contact force is a result of the equilibrium between the skin surface pressure on the plate and the squeeze film force. To run this model, parameters of the plate and the fingertip could be easily identified, whereas contact parameters have to be solved. The resolution in the Fourier domain of the lump parameter model gives the opportunity to simulate fingertip and plate motion. It appears that the higher contact force tightens the gap between the plate and the fingertip and simultaneously connects more the fingertip to the plate, which has a higher skin oscillation. The effect of the ultrasonic vibration is the opposite. A higher amplitude of vibration would widen the gap and reduces the connection between the fingertip and the plate, diminishing then the skin oscillations. The multiscale model helps peer into the contact behavior. It is then possible to estimate the friction coefficient from the impedance measurement. We have compared estimation from the model and friction measurement with a tribometer. This dataset is highly correlated with the R-square of 0.98. The use of a multiscale contact model gives the possibility to estimate also the real contact area. This new achievement opened the door for friction measurement and control on ultrasonic vibrating plate without adding additional sensor. Thank you for your attention.